Design of experiment, DOE. Design of experiment is a modern methodology in which purposefully changes are made in the input variables in order to maximize the yield of the output variables as well as to minimize the number of experiment and noise of the experiment. Why design of experiment? Interaction. With design of experiment, it is possible to detect interaction effect between the input variables. Interpretation. Map of the system may be misleading without using design of experiment. Random noise. Without DOE, design of experiment, it is difficult to assess the noise. Time, cost. DOE require fewer resources for the amount of information obtained, especially as the number of factors increase. So DOE reduce time to design, develop new products and processes, improve performance of existing processes, improve reliability and performance of product, achieve product and process robustness, perform evaluation of material. Design of experiment is useful in the laboratory, the pilot plant and full-scale production and is used for many experimental objectives, including screening, optimization, and robustness testing. An experiment is a test or a series of tests to identify reason of change in some response variables. All experiments are design experiments. Some are poorly designed, some are well designed. For example, study the effect of two hardening process on aluminum alloy, that is oil quenching versus salt water quenching. Objective to determine which quenching solution produce the maximum hardness. Run tests for each solution and compare averages. This is the example of poor design. Before running the experiment, need to know what we are not taking into account. Before running the experiment, need to know other quenching media like air, other factors like temperature of media, number of runs at each combination 2, 3, 5, order of runs, method of data analysis, significant difference in the average. Design, planning how to obtain data from experiment. Description, summarizing the data. Inference, making decision and prediction about the data. History of design of experiment. Design of experiment was first introduced in the early 1920 in a scientist at a small agricultural research station in England. Sir Ronald Fisher showed how one could conduct valid experiment in the presence of many naturally fluctuating conditions such as temperature, soil condition, and rainfall. The design principles that he developed for agricultural experiment have been successfully adapted to industrial and military applications since the 1940s. In the past decade, the application of DOE has gained acceptance in the United States as an essential tool for improving the quality of goods and services. This recognition is partially due to the work of Taguchi, a Japanese quality expert who promoted the use of DOE in designing robust products, those relatively insensitive to environmental fluctuation. It is also due to the recent availability of many user-friendly software packages, improved training, and a cumulative success with DOE applications. When and where DOE is useful? Areas where DOE is used in industrial research, development, and production, optimization of manufacturing processes, optimization of analytical instruments, screening and identification of important factors, robustness testing of methods, robustness testing of products, formulation expert. Here you see a system and here you see the input variables, and here you see the output variable, that is the response, and here you see the control variables and uncontrolled variables. When analyzing a process, experiments are often used to evaluate which process input have a significant impact on the process output, on the response. Actually, why we are doing the design of experiment? Why do we apply the design of experiment on a system? So actually we are looking at which input variable have the significant effect on the response. Design of experiment involves planning and performing a set of experiment to determine the effect of experimental variable on the system. Factors, input variables. Factors are the input variable in the process, also called independent variable, that can be changed by the experimenter. Factors can be classified controllable variables, factors that can be controlled and varied easily during an experiment. For example, furnace temperature, pressure, material moisture. Uncontrollable variable, factors that cannot be controlled in actual operation but may be controlled during experimentation. For example, humidity and air pollution. Here this is the system, this is the input variable or independent variable or factors, and here this is the response or the output of the system, and control variables and uncontrolled variables. Objectives of design of experiment. The primary objectives of the design of experiments are screening, characterization, optimization, and robustness testing. Screening is used at the beginning of experimental procedure. The objective is to explore many factors, to check many factors in order to find whether they have a significant effect on the response, and to identify their appropriate ranges. So, screening are used to see the main effects of the significant factor on the response, and also to see uh, the appropriate ranges, the appropriate levels. Characterization are used to see the main effects of the significant factors on the responses, and the response to see the interaction among the factors. So characterization are two purposes: to see the main effect and to see the interaction effect. Optimization, the objective is to predict the optimum response value for all possible combination of factors within the experimental space or region. Robustness testing, the objective is to ascertain that the method is robust to small fluctuation in the factor levels. What variable are most influential? So that is screening experiments. Setting up X variable for optimal Y, response surface method. Setting up X to minimize variability of Y, robust parameter designs. Setting up X for minimum effect of Z on Y, robust parameter design. Key terminology are basic principle of design of experiment: interaction, randomization, blocking, replication, confounding. Interaction, sometimes factors do not behave the same when they are looked at together as when they are alone. This is called an interaction. Interaction plot can be used to visualize possible interaction between two or more factors. Here you see the slope of this variable and the slope of this variable, they are similar, so having similar slope. Okay, so there is no interaction effect. Here in this case you see they have different kind of slopes, so they have mild interaction. In this case here you see there is strong interaction effect, and here you also see the strong interaction effect. So with the help of design of experiment, we can see the interaction effect among the variables or factors that we couldn't see with one factor at a time experiment. Randomization. Randomization refers to the order in which the trials of an experiment are performed. An randomized sequence helps to eliminate effect of unknown or uncontrolled variables. So with the help of randomization, we can eliminate the effect of unknown or uncontrolled variables. The purpose of randomization is to remove all sources of variation which is not controllable in real life. We all live in a non-stationary world. For example, the manufacturing of a metal part is an operation involving people, machine, measurement, environment. The parts of the machine are not fixed entities. They wear out over a period of time and their accuracy is not constant over time. The attitude of the people who operate the machine vary from time to time. On the other hand, if you believe your process is unstable and without randomization, the result will be misleading and meaningless. By properly randomizing the experiment, we assist in averaging out the effect of noise factor that may be present in the process. In other words, randomization can ensure that all levels of factor have an equal chance of being affected by noise factor or random error. Blocking. The main objective of blocking is to eliminate the unwanted source of variability such as batch-to-batch variability, such as day-to-day variability, such as shift-to-shift variability. The idea is to arrange the similar experimental runs into blocks or groups. The blocks can be batches of raw material, different operators, observation collected under the same experimental condition, that is the same day or the same shift, are said to be in the same block. Blocking is used to eliminate the effect of noise factor and increase the precision of an experiment by breaking the experiment into homogeneous segments. Those are called blocks. Replications. By specifying the number of replicates, util design of experiment, how many times each design point set of experiment condition should be run. Replicates provide you with the ability to compute estimate of power errors. By adding replicates, you are increasing the power of the model. So with the help of replication, you can see the power error, or you can see the standard deviation, and you can find the noise in your experiment. Confounding. Confounding is when the effect of two or more factors are not separable. Confounding occurs when the configuration of high and low factor setting within the test matrix for a control factor is identical to the configuration for an interaction effect. This will occur for at least some interaction in every fractional factorial design. Effects which are confounding are called aliased. Aliases occur when a primary factor and an interaction effect have identical set of high and low among the control factor. One cannot differentiate that the result is due to either the primary factor or the interaction factor. Here in this table you see the factor A, factor B, factor C. These are the primary factors. And here you see A dot B, this is interaction, B dot C, this is again interaction effect, A dot C and A dot BC. Here you see the in fractional factorial design, here you see when the number of factor is 1, here you see plus 1, plus 1, plus 1. And also for the interaction, the 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 type of experiment also we are getting plus 1, plus 1, plus 1. So here you see you could not differentiate the the set of high and low values. So in the number of experiment, here you see the number of factors. So in fractional factorial design, okay, we are getting less number of experiment, but there is the problem of confounding. Major types of design of experiment: one factor at a time, OFAT, full factorial designs, response surface analysis or SM, mixture designs. One factor at a time, OFAT designs. One factor at a time design experiment looking at the impact of different levels of only one factor on the output or response. So in case of OFAT, actually we are looking the effect of one factor on the response using different levels of one factor. Each level of the factor is investigated to see if the response is significantly different from the response at other level of the factor. OFAT is favored by non-expert, especially in situations where the data is cheap and abundant. Disadvantages: OFAT requires more runs for the same precision in effect estimation. OFAT cannot estimate interaction. OFAT can miss optimal setting of factors. Here you see in this diagram, here you see this is full factorial design and this is one factor at a time. And here you see the results. So regarding this diagram, the optimum value is here. But actually the actual optimum value is not at the center, it is here. So with the help, when we are using the OFAT, we couldn't find the optimal setting of factors. Full factorial design. A full factorial design is applied when the purpose is to determine which factors are more important in the study and the range of values of those factors. This is the only design that can evaluate interaction among all factors. The effect that the main factors and all the interaction between factors are measured in full factorial design. Disadvantages: it is not possible to find the optimum value using full factorial design. Okay, with the help of using full factorial design, we can see uh, the main effect as well as interaction effect, but we couldn't find the optimum value by using the full factorial design. So a factorial design can determine the main effect of the factors, determine the effect of iteration among the factors. Disadvantages of full factorial design: the number of experiments increase exponentially. Time consuming. Do not tell us any information about the optimum value. Costly because number of experiments increase. The factorial model equation, here you see this is the response. Here this is B naught coefficient, this is the constant, plus summation I, and this is Bixi, and this is the interaction. So this is the main effect, here this is the interaction effect, and here this is the random error. For two factors, here you see B naught, B1 x1, B2 x2, this is the main effect, plus B1 B1 2 x1 x2, this is the interaction, and here this is the error shown. Fractional factorial design. Fractional factorials are different designs used to screen many factors to find the few that are significant, but they may be lead to compromise when looking into interaction effect. There is a problem in fractional factorial design, that is the confounding. Okay, with the help of fractional factorial design, we can see the main effect, but sometimes we have to compromise to see the interaction effect. Fractional factorial design are having three types of resolution. Resolution 5 designs can find main effects, two-way interaction, and three-way interaction. Since three-way interaction are not common, most fractional factorial design use either resolution 3 or 4. Resolution 4 design require more run, but can find the main effects and a two-way interaction. In case of resolution 5, we see the main effect, two-way interaction, and three-way interaction. While in case of resolution 4, we see the main effect and only two-way interaction. Resolution 3 designs have the smallest number of runs, but can only isolate the main effect of the factor. Iteration terms cannot be identified. So here you see the magnitude of confounding is the maximum one. Here we couldn't see the interaction effect, but we can see the main effect. What is meant by resolution? Resolution is the measure of the degree of confounding for main effects in a fractional factorial design. Response surface methodology. Response surface methodology designs are useful for analyzing problem where several factors influence a response and the goal is to optimize the response. So in case of response surface methodology, we are looking for the optimization. We are looking for the surface at which the optimum value is, is existing. RSM answers different kind of questions such as how is a particular response affected by a given set of input variables or some specified region of interest? To what level the input are to be controlled to give a product simultaneously satisfying desired specification? What values of inputs will yield a maximum for a specific response? And what is the nature of response surface close to the maximum? The eventual objective of the RSM is to determine the optimum operating condition for the system or to determine a region of the vector space in which operating requirements are satisfied. The analysis of response surface can be thought of as climbing a hill where the top of the hill represents the point of maximum response. If the true optimum is a point of minimum response, then we may think of descending into valley. Response surface methodology, response surface methodology, these are second order model. A second order model utilized in response surface methodology. Here you see this is the response, constant, main effect, and here you see this is the quadratic because here you see the square term. So in response surface methodology, we are looking for the curvature. So here is the quadratic term is included. And after that, also the interaction and random error. Example for three factors, here you see y is equal to b0 plus b1 x1, b2 x2, b3 x3, and here you see b11 x1 square, b22 x2 square, b33 x3 square, and here you see the interaction term. These are the interaction term and this is the error. Why not to use response surface methodology from the beginning? Adding center point from the beginning means that the number of experimental run will increase due to the increase in levels. Our aim from design of experiment to save time, efforts, and cost. There are different types of response surface design. In this lecture, I'm not going to explain each type of design. In the next video, inshallah, I will discuss each type of design along with example and also using the software. Mixture designs. Mixture design experiment are a special class of response surface experiment in which the product under investigation is made up of several components or ingredients. Design for this experiment are useful because many products designs and development activities in industrial situation involve formulation or mixture. In these situations, the response is a function of proportion of the different ingredient in the mixture. For example, you might be developing a pancake mixture that is made of flour, baking powder, milk, egg, and oil. You might be developing an insecticide that blends 4 chemical ingredients. In the simplest mixture design, the quality performance of the product based on some criteria depends on the relative proportion of the mixture component. The amount of component measured in weight, volume, or some other units add up to common total. In contrast, in a factorial design, the response values depend on the amount of each factor. How? In mixture design of experiment, the measured response is assumed to depend only on the relative proportion of the ingredient or component in the mixture. For example, if you want to optimize the tensile strength of stainless steel, The factors of interest might be proportion of iron, copper, nickel, and chromium in the Li. The fact that the proportion of the different factors must be, the total sum of the proportion should be equal to 100. So mixture designs are used when the response changes as a function of the relative proportion of the components. All components must be entered in the same unit of measure and each run must sum the same total. So here the total we keep constant. Planning a mixture experimental involves the following: define the objective of the experiment, select the mixture component and any other factors to be studied. Other factors may include process variable or the total amount of the mixture, identify any constraint on the mixture components or other factors in order to specify the experimental regions, identify the response variable to be measured, propose an appropriate model for modeling the response data as a function of the mixture component and other factors selected for the experiment. Select the experimental design that is sufficient not only to fit the proposed model but which allow a test of model adequacy as well. So in case of mixture design, what we have to keep, the total concentration of the mixture is keep constant. Okay, the concentration of ingredient that you can vary, that you can change, but the total concentration of the mixture should be keep constant.